Hey everyone, welcome back to Signal Processing with Paul, and in this video what I want to do is talk about why integrals are easy in Fourier Land. So this would basically be whether you're using Fourier series or the Fourier transform, depending on whether you have a periodic signal or not. Why is it so much easier to take the integral in Fourier Land? Where does this come from? How do we do integrals? So suppose I have some signal x of t, and I want to know what its integral is, so what the integral of x of t is. I may not know what this is. This may be very difficult to solve. But I do know that if I move from x of t to x of f using the Fourier transform or the positive Fourier transform, it'll be very easy for me to do some manipulation on x so that we have some function that's a manipulation on x of f, and then all we need to do is simply take the inverse Fourier transform to get back, and now I've done this integration without needing to do all the nasty integration tables or whatever we don't want to do. So sometimes I ask students, do you guys like doing integrals? Some of them do actually, but if you don't, or you're lazy or you don't want to do it numerically, this is a great way to do it without needing to spend a lot of work doing it by once again taking this transform, doing a little manipulation, and taking it back. So the thing to remember is that x of f is defined in the Fourier transform case as equal to the integral from minus, well, actually, let's do it this way. Let me say that x of t is equal to the integral from minus infinity to infinity of x of f, this is like capital X, e to the plus j 2 pi f t with respect to f. And likewise, x of t, I'm just going to put p for periodic, is equal to the sum from k equals minus infinity to infinity of c sub k, our Fourier coefficients, times e to the j 2 pi kt over t. So if I want to take an integral with respect, if I want to integrate this with respect to t, the integral of this with respect to t, dt, is basically the same as if I took the integral of all this stuff with respect to t. But notice how the only thing that depends on time is just this particular piece in each of these cases. So we can, of course, bring the integral inside and just say the integral of x of t with respect to time is basically equal to the integral, now this is the f integral, times the integral of e to the j 2 pi f t with respect to time, now with respect to frequency. And of course, notice that, the integral, in our case, of e to the theta t dt is equal to 1 over theta e to the theta t, where theta is just everything that's not t. So in this particular case, what we see is that this is equal to the integral from minus infinity to infinity of x of f 1 over j 2 pi, j 2 pi f times e to the j 2 pi ft df. So what this is basically telling us is we just multiply what we have in the frequency domain by 1 over j 2 pi f. So we get x of f. Now if we want to do the integral, we do this times 1 over j 2 pi f. It's getting a little small to see. And similarly for the Fourier series case, once again, the integral that we have with respect to time is going to only affect this particular component. And we see the exact, this is going to be this. The integral that we have is only with respect to time. So we see the exact same thing. We get this equals the sum from k equals minus infinity to infinity of t over j 2 pi k. Of course, we have our c sub k here, times e to the j 2 pi kt over big T. So we're taking the integral with respect to time. So we get this. And similarly, once again, if this is the Fourier transform, we get 1 over j 2 pi f times x of f. Or in the case of the Fourier series, we get t over j 2 pi k times c sub k. So in either case, what we see here is just simply a constant factor multiplied. And notice how if we looked at in the last video when we did derivatives, we have the exact opposite. We had j over 2 pi times k, or we had, of course, j 2 pi f in the numerator, and here we have 1 over that. So what we see here is, of course, integrals and derivatives basically being reciprocal multiplications of each other. And if you wanted to do a second integral, you simply take this value and you square it. Or you want to do an nth integral, you just simply take this to the power of n and multiply it by your frequency component. Notice how these things are so easy, but the reason it's so easy is that it was constructed to do this. We wrote our signal as a sum of complex exponentials, which we know how to take derivatives and integrals of. They're the easiest functions we can imagine to take the integrals and derivatives of, so this is one of the reasons we built it in this particular way. So hopefully, once again, using this as a way, using Fourier series or Fourier Land as a way to represent change with respect to time makes a lot of these things a lot easier to do, and that's the whole beauty and benefit of it. So hope you found this helpful, and I will see you in the next video.